to look specifically at how electrons are arranged in the atom. So in order to do this, we are going to need to understand energy levels. We're going to need to explore emission spectra. We're going to look at the colours obtained from the flame test to explain energy levels. We're going to discuss energy sublevels, how they're filled, and the shape of different orbitals. And then we're going to look at Heisenberg's uncertainty principle. So in our previous videos, we've looked at the discovery of the proton, the electron, and the neutron, but we didn't really look at the structure of the atom. It was briefly looked at by Thomson with his plum pudding model and Rutherford with the gold foil experiment, but it wasn't until Niels Bohr came along that there was actually a thorough understanding. So Bohr began by studying spectra. Now, before we can go into what Bohr actually done, we need to understand where spectra come from. And when white light is passed through a prism, the light is broken up into a continuous spectrum of colour. And we can see here that the continuous spectrum of colour is actually a rainbow. So what Bohr done was Bohr tried this idea, but he tried it with a hydrogen discharge tube, which is simply a tube filled with hydrogen gas at low pressure and electric current is able to pass through it. And he found that for hydrogen, instead of a continuous spectrum, he obtained different coloured lines spaced out, and he called this an emission line spectrum. The different colours correspond to different energy wavelengths, and he saw that when he tried this with different elements apart from hydrogen, that they gave different spectra. So this is a diagram to help explain what I've been talking about on the last slide. So we had the hydrogen gas here in a gas tube. It was passed through a prism, and instead of a continuous spectrum, we got a line spectrum with a violet, a blue, and a yellow colour. And this is an example of an emission spectrum here, with the black background and the coloured lines on it. Now, as we said in the last slide, there was different spectra obtained for different elements, so that tells us that each element has its own unique line spectrum. And Bohr realised that a model of the atom must explain the following. It must explain why emission spectra are lines rather than continuous, as we get with white light, and he must be able to explain why each element has a unique spectrum. And spectra can be studied using a spectrometer, and that's discussed in another video. There's a short experiment on the Leaving Cert course that shows the colours that different elements emit, and this is called the flame test. And the flame test looks at the salts of lithium, sodium, potassium, barium, strontium and copper. In the past this has come up and the steps have been asked, so it's important to know these. So a wooden splint is placed in water overnight. The next day, the damp wooden splint is dipped into the salt. The wooden splint with the salt sample is held over the blue flame on the Bunsen burner, that's important, and you observe the colour that is obtained. So here are the results. The lithium metal gives a crimson colour. The potassium metal gives lilac, and that's indicated by number 3 here. The crimson is number 2. Barium gives a green colour, strontium gives a red colour, copper gives a blue-green colour as indicated by number 4 here, and sodium gives a yellow colour as indicated by this separate picture. And you will see these colours in fireworks, as the various colours in fireworks displays are obtained by adding salts of various metals to the explosive mixture in fireworks. So up until Bohr's studies of spectra, scientists thought that electrons in an atom could have any energy value. However, Bohr's theory introduced the idea of quantization, and that means that electrons have fixed amounts of energy within an atom. And this fixed amount of energy is called a quantum of energy. So from studying the spectra, Bohr proposed that the single electron of hydrogen could only occupy certain energy levels, and he called these orbits. And electrons are found in these energy levels as they revolve around the nucleus. The energy levels are represented by the letter N, where N is the number from 1 to infinity. So if N is 1, that is shell 1. If N is 2, that is shell 2, etc. And shell 1 is the one that is closest to the nucleus and has the lowest energy. So here's a definition for an energy level. An energy level is defined as the fixed energy value or the fixed amount of energy that an electron in an atom may have, and this needs to be known for the exam. Now, atoms normally exist in something called the ground state, and this is when the electrons occupy the lowest energy level that is available. So for example, in hydrogen, the ground state is when the electron is in n equals 1. However, sometimes energy can be gained or lost, and if energy is gained, your electron will jump from the ground state into something called the excited state. And this is your definition for the excited state. The excited state of an atom is one in which the electron occupies higher energy levels than that of the ground state. And it's very important to know that the excited state is very unstable. So in hydrogen, an example of the excited state would be n equals 2. So here I've explained it in a diagram for you. This is hydrogen in its ground state because it's in n equals 1, as it is in the closest shell to the nucleus. And here it's in n equals 2. So the electron has gained energy to move into the n equals 2 energy level, and it has gained that energy from this photon of light here. So to further explain that, when an atom is given a quantum of energy or given a certain amount of energy, this energy can be absorbed and will cause the electron to jump into a higher energy level called the excited state. The energy absorbed is equal to the difference in the energy between the lower level and the higher energy level. So that means that this energy, or the amount of energy here, is equal to the amount of energy absorbed by the electron. So if I highlight that for you, this energy here from the light is equal to the energy absorbed. Similarly, if the electron is in the excited state, as it is in the right-hand diagram, the energy that is released to allow the electron back down to the ground state is equal to the energy emitted, and it's emitted as a photon of light. So, as we've said, electrons don't last very long in the excited state because the excited state is unstable. The extra energy that is emitted as the electron falls from the excited state to the ground state is emitted in the form of a photon of light with definite frequency, and I've spoken about that in the last slide. And this is where the light on the emission spectrum comes from. Electrons gaining energy and going up to the excited state, and when they fall back down to the ground state, they emit the light that we see in the emission spectrum. So, since only definite energies are emitted, electrons can only occupy definite energy levels. So this frequency of light that is emitted and that we see in the emission spectrum can be calculated using this formula here, where E2 stands for the energy of the higher energy level, i.e. the excited state. E1 is the energy of the lower energy level, which we know as the ground state. H is a constant called Planck's constant, and F is the frequency of light that is emitted. So this formula can be rearranged to get F on its own. And now we can explain why each element has a unique emission spectrum. It's because each element has a different number of electrons. So that means their arrangement will be different. So that means different frequencies of light will be given out. Similarly, there's a few different series that you need to know for your Leaving Cert. So we've got the Paschkin series, which goes from energy level n equals 5 to n equals 3. So if the electron falls from n equals 5 to n equals 3, that's found in the infrared region and it is invisible. The Balmer series deals with electrons falling from the n equals 5 to the n equals 2 and the n equals 3 to the n equals 2, and this is visible. And the Lyman series deals with anything falling from n equals 2 to n equals 1, and this is invisible and found in the UV region. So further on from this then, a scientist called Broglie suggested that all moving particles had a wave nature. So it was important that atomic structure described electrons as behaving as waves and particles. So Bohr had a simple circular structure where Broglie wanted a wave structure. So this had implications for Bohr's theory, which stated that electrons travelled along a precise path at a precise distance from the nucleus. So here they had a precise path, but here they are different distances from the nucleus due to their wave nature. And this problem was dealt by a scientist called Heisenberg. So Heisenberg came up with his uncertainty principle that states it is impossible to measure the velocity and the position of an electron at the same time. He said that we could only talk about the probability of finding an electron at a particular position in atoms. So Bohr's simple circular orbitals were replaced in the hydrogen atom, and his calculations and shapes gave us the shapes of atomic orbitals, which we will discuss now. So the first thing is, what is an atomic orbital? An atomic orbital is a region of space around the nucleus of an atom where there is a high possibility of finding an electron. And this is a definition, so it's very important that this is learned off. Now, there is 4 different types of atomic orbitals. There's S, P, D, and F. So if we start with S orbitals are spherical in shape. They differ only in size and can hold up to 2 electrons. And this is the diagram here. Next we've got p orbitals, and p orbitals are dumbbell shaped, and there is 3 p orbitals, the px, the py, and the pz, each holding 2, so there is a total of 6 electrons in the p orbital. And p orbitals can have sigma and pi bonding, which I'll discuss in the next slide. And this diagram here is important as you could be asked to draw the different shapes of the p orbitals. So here you can see a sigma bond, and a sigma bond is when you have head-on overlap of orbitals, so the 2 ends of orbitals collide, and a pi bond is when you have sideways overlap, so the 2 sides of your atomic orbital overlap. The third type of orbital is the d orbital, and there is 5 d orbitals, each holding 2 electrons, so there is 10 in total. This diagram here is just to show you what they look like, but you don't need to be able to draw this. So as time went on, scientists were able to look more closely at spectra, and what it was actually discovered was that what appeared as one line was actually multiple lines on spectra. So it was proposed that each main energy level was actually made up of many sublevels that were very close together in energy. The number of sublevels was the same as the value of n for the main energy level. So, for example, n equals 2 has 2 sublevels and n equals 3 has 3 sublevels. So a sublevel is just a subdivision of a main energy level. So finally, your definition for an energy sublevel. An energy sublevel is a subdivision of a main energy level that consists of a group of 1 or more orbitals of the same energy. So this here is an energy sublevel diagram, and as you can see, if we start at the bottom, we have n equals 1, and as you can see there is one energy sublevel there, and that is the 1s. If we move up to the next one, n equals 2, we can see that there is two energy sublevels. There is the 2s and the 2p. Now these are separated out a little bit just to help understanding, but they are very, very close in energy. Next, we'll look at the n equals 3. So the main energy level is 3, so we would expect 3 sublevels, and that's what we have. We've got 3s, 3p, and 3d, and as you can see here, the 3p is split into 3 little circles. So this is the 3px orbital, the 3py, and the 3pz. Now again, there's a gap between the 3p and the 3d, but they are very close in energy. Next, as we move up further, we get to the n equals 4 energy level, and as you can see with the n equals 4, the important thing to note here is that the 4s is lower than the 3d, and we will look at this in the next video on electronic configuration. So the last thing we want to do is we want to understand the difference between a sublevel and an orbital. So an energy sublevel is a subdivision of a main energy level and consists of a group of one or more orbitals of the same energy. Where an orbital is a region of space around the nucleus of an atom where there is a high possibility of finding an electron. So the easiest way to do this is to look at an example. So if I take a main energy level of n equals 2, that main energy level has two sublevels. So there is two sublevels, and those two sublevels are the 2s and the 2p. And then it is made up of 4 orbitals, and the 4 orbitals are the 2 people out. So that's it for this video. Make sure you read